our guest speaker a few moments ago how it was 20 years ago that we were in the parking lot A right over here talking about the role of computers in energy. And at the time, we were really talking about what might be the role of computers in energy. We knew that computers were out and PCs had sort of just been introduced to the general public at that time, but actually how they might be used in the energy field, nobody really knew. We had some sort of vague ideas of how they might be used, but how much impact they would have on buildings, we of course had no idea. And what impact they'll have in the future, probably you folks have no idea. But definitely a lot has happened in the last 20 years. And Mike Gabel's been right in the thick of it all along. So Mike's been a consultant for many, many moves in the energy business and has really laid the groundwork for a lot of the things that many of you are studying in your class, especially in the computer applications and energy management and design class. So Michael's done a lot of nitty-gritty work way back on the Comply 24 software and helping develop energy standards in the state of California. He's been a consultant for over 1,000 clients in the energy field, so he's obviously doing this a lot in many different ways. Got his master's degree in architecture at UC Berkeley, but really his education, I know, has been primarily in the field, working day-to-day with many, many clients. He's done professional trainings, he's written training manuals, he's written software, he's been a leader in the energy management profession in the state of California, and has actually been an employer of a fair number of our graduates who live here as well. So in many ways, he's been a major contributor to the energy field in the state of California, and what happens in California has a major impact on the rest of the nation around the world. So we're delighted to have him here today. He's going to talk about a broad topic, which is California energy efficiency standards, past, present, and future. He's probably the guy in the state that knows more than any. So we're lucky to have him here, and I'd like you to join me and welcome Mike Gabel to the stage.
Thank you. Very kind words, Rocky. A little bit overstated, but I won't hold it against you. The last time I was here, a couple of years ago, Rocky gave me a quick tour of the building before it was actually commissioned and started being used. And it's nice to actually be in the space finally after all the years of planning and hard work that Rocky and the staff at Sonoma State have put in developing the center. As Rocky said, it's been a long time since we first met, and here we are 20 years later, and we're still at it, which you can interpret a lot of different ways, but we won't go there. I guess what I wanted to do today was give everybody kind of an overview survey of the energy code in relation to things that were going on at the time that created it and what's going on now and potentially what's probably going to be occurring or may be occurring in the coming years. I'm going to see if this works here. Obviously, the energy crisis, so-called, has been around a long time, up and down over many years. And in terms of peak power, also in the last 4 or 5 years, that's been a big issue. And obviously, conservation, as many of you have learned and studied over the last several years at school and prior to that, is an enormously important aspect of the whole thing. I mean, conservation still doesn't get the press of hydrogen vehicles and solar power and some other things, but it's been at the core of environmental, really, progress in the last many decades. And I want to sort of talk a little bit about that in the context of the standards. There are sort of several different ways in which you can understand the standards, the energy codes, known as Title 24 in California. And what I want to do is kind of weave into this discussion, this is kind of freewheeling and kind of open, issues about research and technology that have been moving forward over the last many decades. There's political and governmental aspects and policy aspects I want to mention. There's obviously economics, and in recent years, market manipulation, which we heard about in the last couple of years about some producers as they relate to California energy supplies. The global environmental science itself, I'm sure some of you know a lot more than I do probably because you've been studying it more intensely, but there's some conversions of things we've learned over time. And finally, the progress of the energy code itself in terms of where it started and where we are now and where we're going. And so kind of how we got here, what's going on now, and what's likely to happen soon. And finally, I'll try to wrap it up if we have time. I'll get you all out of here by the 10 to 6 that Rocky says is your deadline. Just a couple of things. if you have a question, please raise your hand, and I'll be happy to take questions as we go. If it's not quite relevant, or if I need to move on, I'll worry about that. But if you have a question, please feel free to ask the question, because we have enough time to kind of be a little bit leisurely about moving through some of these ideas. I was listening to NPR about 6 months ago, and I didn't even know myself. I thought that the guys who were doing global warming papers in the 70s were the first ones, but it turns out there was a German, you probably know this, there's a German scientist in 1938, right before World War II, who was doing calculations, and he decided that, based on his sort of back-of-the-envelope calculations, that CO2 was going to continue increasing if human population increased with sort of corollary industrial pollution and activity. And he basically was the first one and published a paper and introduced it in 1938 of global warming. So it's been a long time since someone got the idea that this was something that was possibly going to happen. The real shock to our world that most of you are not old enough to remember, but some of us are, happened a little over 30 years ago. And it was another Middle East war, because there had been several before then. But in this case, in '73, the Arab countries decided to use their economic clout to band together and created essentially an embargo of oil to the United States and other countries, and drove up the price of oil and other related products dramatically, and it really shook everybody to the core. Now, it's hard now for us, looking back on this time, to really remember what that felt like, but it was just sort of out of the blue. It wasn't obviously quite as dramatic as 9/11, but it was as dramatic in terms of it coming out of the blue in a way in which people just didn't expect it and had no preparation for and hadn't thought about. So it was kind of a big shock wave that took a long time to sort itself out. What happened in California is shortly thereafter, two state senators, Warren and Alquist, created legislation in California, a state legislation which created the California Energy Commission, really for energy stability and for cost-effective energy standards that would help keep energy usage, the cost of energy uses, essentially low to not over-impact the economy. So really, to some degree, I would argue it was a political decision, but it was sort of an economic decision to sort of keep the California economy going. And it was Governor Ronald Reagan at the time who signed the legislation. So this was really a bipartisan response to what happened in the early days. In 1978, the California standards, as we know them, took effect for the first time. And there's one key aspect to this which I want to point out, which is very unique, which is that California has standards which penalize electric resistance source energy for space heating and water heating. And because the environmental impact of generating electricity is, as you know, significant in relation to, say, burning natural gas on the site. Well, we still have it in the state, and it's still the only state in the country that has this, and it's an enormously progressive and important break from what the rest of the country has been doing and is still doing today. And it's interesting because, the politics of the time allowed it. Some people say, well, I once asked somebody recently, how did the utility companies allow this? Because everywhere else in the country, the utility companies have vetoed it. Well, PG&E was the biggest player, and PG&E was Pacific Gas and Electric. They figured they got people coming and going. They didn't care, so they figured, all right, we'll be progressive and we'll give this up. And so it was a really important aspect of the standards, which I'll talk more about later. In the 80s, what started happening is we started getting significant improvements in technologies. Lawrence Berkeley Laboratory was developing low emittance coatings for windows, compact fluorescent lighting technology, high-efficiency mechanical systems were developed by Carrier and some other people. And as Rocky pointed out, we started getting into analytic methods. These are computer simulations of building and building performance that were beginning to be ported over to PCs. And again, some of you, the PC was a big deal. I had an Osborne computer that had 64K of RAM, and that was really hot, and we were all pretty excited about it. But it was just sort of the beginning of taking big mainframe computer programs like DOE2 and other programs and trying to get them to squeeze them down to run on small PCs. By the late 80s, what had happened was ozone became a big issue, which isn't directly connected to global warming, I mean, in the sense of its own sort of track, but the reality of a global phenomena that was dangerous to the welfare of the human population and all the, the whole ecosystem became apparent, and global environmental impact and global politics started beginning to apply, really, I would say. We can debate the dates exactly, but this was a stream that was really unique and unusual, because prior to that, it really wasn't a global pressure for environmental reform and for these sorts of things. They tend to be more political and economic. By the 90s, Nobel Prize winners from all over the world and all scientific disciplines were pretty much agreeing global warming was very likely, if not definite. And so you had both the science kicking in, and you also had the politics of the pressure being put on governments to do something about global warming, and specifically from CO2. So that sort of sets the stage a little bit for what happened in the late 90s, and I'll just mention deregulation. People kind of remember that one. That wasn't that long ago. Essentially, the utility companies and a lot of legislators were convinced that this was the greatest thing since sliced bread, and the state legislature deregulated the utility companies, broke them up vertically, and so you had sort of the economics and the politics and the environmental issues all sort of in the pot. And by 2000, really 2001 especially, but even 2000, it was very clear that there were major problems with deregulation. It was clear that we had a power crisis. No one knew the real reasons for it at the time. People guessed. And we had terrible, soaring prices and blackouts and brownouts. And now we know conclusively, in my humble opinion, it's pretty well established that there was market manipulation going on, in addition to everything else that was driving the equation. So those are some sort of highlights of what's been going on. What's interesting to me, and what I wanted to point out from all of this, is that in the old days, let's call it, in the 70s and the 80s, some of us who got into this really had no ammunition, and there was no awareness or agreement that there were actual tangible and measurable global impacts that were adversely affecting the human civilization throughout the world and all the ecosystems. But it was more of a national and statewide issue about energy independence and economic sustainability and so forth. California was unique, as I said, in its environmental impact sort of forethought. But now, after all this time, it's become clear the reasons for why we conserve is, there are a lot more reasons, and a lot more compelling reasons than what we all sort of envisioned in the early days. And so you could all say we were either just lucky, or we were smart, or just that's the way things worked out. But the first energy crisis kind of got us going. And that's kind of the history. Now, let me just stop for a second. Any comments or questions about history or how we got here? Just, all right. Yeah.
And they commuted daily without how to work things. Where we live, and when that energy crisis hit, they never thought about the cost of fuel as something, and that wasn't a big shock.
Yeah, I mean, the comment is about, at the time, people were very, very shocked and upset about the cost of gas. And we may have another one of those coming soon, and we'll talk about that. But SUVs may yet go out of style for reasons that are unanticipated up until now. But yeah, I mean, so here we are today, and we're looking back. And I guess what I want to do now is mention a few kinds of conservations, because this isn't always obvious. When people talk about conservation, to me, I've kind of grouped these into three categories: lifestyle and individual behavior. Now, when Jimmy Carter was the president in the 70s, he got really ridiculed for suggesting to people that they turn the thermostats down as a first line of defense against increasing your utility bills. However, it's really legitimate, and in fact, the recent energy crisis in 2000-2001 proved that there's a kind of an elasticity of 10 or 20% that users can, just by changing their lifestyle, reduce energy usage by an enormous amount just by making conscious choices. So thermostat settings, refrigerators, cleaning the coils of your refrigerator, water heater usage, programmable thermostats, how much you use. You remember to turn off your TVs and stuff, and turning off your computers as well. These are all things which actually do add up, it turns out, as we learned in the last 5 years. So that's kind of one category. Let's call it individual behavior and responsibility. You can do a lot just in that. There's a second level, I would say, about maintenance and repairs and low-cost improvements where people who are even renters in an apartment or other people can do very simply. And that is replacing air filters, vacuuming coils and refrigerators, installing thermostats. That requires going out and buying them, replacing incandescents with compact fluorescents, and all those hundreds of good things that you can do that don't take a lot of money. They take sometimes a little time, but again, they collectively can add up to a significant amount of energy savings and so forth. The final category are what I call major improvements to buildings and appliances, which is the case of major renovations and new construction. And this is all new stuff in buildings, which is insulation, windows, big appliances, new appliances, water heaters, HVAC, lighting and controls, time of use meters. And the Building Energy Code was really designed to deal with this level of conservation. The idea was if you can get all this good, efficient stuff into buildings, you at least, people can always do the other first two things on their own in a crisis. But obviously when there's suddenly blackouts and brownouts, no one's going to be running out immediately the next day and buying all new windows and installing them the next day. And it's also too costly, and people rent and they don't own. And there are all these other infrastructure issues which have to do with long-term design decisions and so forth. So just to sort of frame that, because that's something that you don't really think about much in terms of conservation, but there's all these different levels that I wanted to sort of bring up.
Mike, let me jump in for a second.
Sure.
One of the students just went to see Ralph Kavanaugh and some other folks from NRDC down at the PPC looking at the role of energy efficiency in California's new energy market. And in 2001, during the first month of that crisis, we reduced peak demand by 5,000 megawatts. So that's well over 5 large power plants, 1,000 megawatt coal-fired or 1,000 megawatt nuclear power plant. They're not going to run at full capacity. So 5, 6, 7, 8 large power plants. That's the equivalent of what we were able in 1 month's time, not through maintenance and repairs or new appliances, but just through behavioral changes in terms of reduction. So that, according to their calculations, converted 50 to 160 hours of rolling blackouts, reduced CO2 emissions, the equivalent of taking 1/3 of Bay Area vehicles off the road for an entire year. So anyway, people say everything's been done to be able to save energy. When the price goes up, like I said, there isn't elasticity of demand. People find ways to do things differently. So that's just from 2 summers ago.
Good. Thanks, Doctor. What I want to do now is I've sort of introduced the subject of what the standards cover generally. I want to kind of go back, take a breath, and give a little history with a little flavor too. It comes from the days when I was intimately involved in. I used to be a workaholic. I'm not anymore, but I was very involved in our work and everything we were doing in the old days. And try to frame this. When you look back at something, it looks like it's an inevitable, obvious thing that was done. But at the time, it's not inevitable, it's not obvious at all. And so I want to kind of give a sense of where we've been. When the standards took effect in '78, I was just starting graduate school at UC Berkeley, and I was hearing about them. And basically what it turned out was that a few building officials kind of heard about them, maybe about 5 or 10%. And they wanted to see some forms turned in to show that you'd met the code. And they didn't look at the forms. They didn't check the calculations. I'd say 10% maybe sort of asked for them. If you didn't have them, they didn't say anything. It was kind of a joke. It was a bit discouraging to some of us who were kind of hoping it would be more than that. The building industry was very upset about the standards because all they saw was it increased their first cost, as it always does and as it always have. And the state standards were not very clear. The manuals that go with the standards were also unclear. it was, as I said, it was the Wild West. It was kind of the first time that the state had energy codes. No one knew what the heck was going on, and it was interesting, but it was a little bit discouraging. The forms themselves were kind of unintelligible, and people were disreputable. People were doing calculations that actually made no sense, but seemed to give credence to some builder who wanted to put 50% glass in his house, single pane clear with no shading, and they somehow gave in paper that justified it. So I think a lot of us in the early days, and a lot of the Energy Commission itself, a lot of people started realizing this is not working. And I personally felt, getting out of graduate school in '81, that if I was going to be involved in this field, if I didn't try to help clean up the mess, I wasn't sure I could stomach staying in the business, because I didn't want to be part of something that was really kind of bogus and really ineffective, essentially. Now, just most of you know this. How many people have taken Chuck Clemens' course or are taking it? Either have or okay. So this is kind of some stuff some of you know, but some of you don't know. The structure of the energy code hasn't changed in 25 years, and that is there's stuff called mandatory measures. That's stuff that every building of a certain occupancy type has to have certain things at a minimum. And then you have to show an additional overall energy use compliance using a so-called prescriptive approach or performance approach. A prescriptive approach is just a list of prescribed measures that the building has to meet what's called the energy budget. And if you can't do a prescriptive approach because something about your building doesn't fit this rigid set of requirements, you do an analysis, or have someone do an analysis, which shows the overall building meets the requisite amount of energy use. And you can do trade-offs between different measures. So conceptually, as a concept, this has been there since the beginning. Everyone understood, building officials, they understood mandatory measures. So mandatory measures in the old days, that was the one thing a lot of them did look for. Is there insulation in the wall? All right. Is the furnace 80%, or is it certified? All right. I mean, it's very simple kind of checklist stuff. They could do it. But the rest of the stuff, whether the building as a whole, whether it's a house or this building, whether a building met the code overall, I mean, they didn't have a clue. And a lot of people just didn't understand how it worked. Let's see. So what happened is, after the first, say, few years in '78, they started immediately working on a second generation of standards, which they felt had to be implemented to improve the situation. And there were a lot of key and important issues that were resolved. First of all, we had a new residential manual to explain the standards. And I was actually co-author of that, and I worked many long hours for basically no pay to try to make the standards accessible and clear, with some success. The big breakthrough was that, I don't want to get too technical, but basically up until '88, there were very Mickey Mouse kind of standard energy budgets for houses that didn't actually correspond to the exact house you were building. So there was sort of a technical problem and inconsistency. And what we established was custom budgets for each house and each building, where if you're building a house, you simulate the performance of that house with hourly weather data and with a certain program, and you compare your house to essentially the same exact house with the certain specific energy measures in it. So it was a kind of a really fine-tuned technical leveling the playing field for establishing a budget. Standardized forms. Believe it or not, in the old days, all the computer programs that were approved printed out their own different forms. So that was really popular with the building officials, I can tell you. That was drove them crazy. I mean, they just threw up their hands and say, we couldn't do it. But by '88, it was obvious to everybody we had to have standard forms people could interpret. And other improvements to software and computers, which Rocky alluded to, starting in '84, we were moving up the learning curve on that stuff. How many people know there's the program called Energy Pro, some of you use? So the MS-DOS ancestor legacy version of that was called Comply 24, and that was what I conceived on a vacation in 1983 up in Yosemite. I was on vacation. I thought of that. So it's been a long time. These things have been developed over a long time. Then what happened is for about 3 or 4 years later, the non-residential standards adopted the same basic philosophy as the residential standards. You know, residential is one occupancy, essentially. Non-residential, how many do you have? Retail, office, school, grocery, gymnasium. I mean, you have dozens of non-residential occupancies. So we took the experience from what we had learned and applied it to, I was involved in the contract with the Energy Commission to take all the rules about the standards and put them into the compliance software so that it would generate the correct energy budgets for all kinds of buildings. And by the way, in this period, it became very clear that after 88, it became clear this stuff was working. In other words, by 88, 89, in this period here, it was obvious that we had basically solved the major problems. And in the residential, and we wanted to go back and solve it for non-residential. So we were starting to succeed, and it was getting very interesting. And what happened in the early 90s is PCs started running faster and faster, where how many people know of what's called the DOE2 program, the DOE2 simulation? Anybody heard of that? Rocky, okay. It's the grandfather original U.S. Department of Energy, DOE, sponsored Fortran program that simulates building, thermal simulations. That is, it's buried under Energy Pro. You don't know what's in there, but it's in there. But it used to take 8 or 10 hours to run on a PC. So it was a little discouraging if you put in the wrong input and you set it running overnight and you come in the morning and then you discover it blew out, or you put in the wrong input. Well, you got another 8 hours to rerun. So what happened in the early 90s was that the runtime started dropping down to 15 or 20 minutes or less. And I'm just giving you kind of a free association here, because these are all factors that sort of came together. And it made a big difference. Suddenly you get this really powerful program now running on a PC in literally a few minutes, and now it's just a few seconds on your 3 gigahertz laptop. So all of these, there's kind of a convergence of a lot of things going on. Technology continued to improve in the 90s. The cost of compact fluorescents and T8s, lamp fluorescent fixtures, these are what, T5s? T5s, yeah. But all this stuff kind of dropping in cost. The low E coatings, which had been invented in the 80s, really started coming down in price, became really cost effective and competitive with other windows. HVAC controls and high efficiency equipment also. All this stuff. So you had the ability to start simulating things really fast, better technology, better standards, and suddenly the whole game was really changing pretty dramatically.
The user's manual for the DO2 software was like 3 linear feet on the bookshelf. You're lucky to have it embedded in Energy Pro. Not worried about it.
Yeah, actually, let me digress for a minute. It's worth mentioning these things in terms of user-friendly and unfriendly. The simulations that were developed like DOE2, even to some extent the CalRes program, which used to be called CalPass, and the predecessor to the Energy 10. You guys have used Energy 10. Have you ever heard of it? A little bit, some of you. Okay. So some of these programs have predecessor versions or early versions that had command language structures in Unix. I mean, you had to sit there typing into the computer these arcane syntax, syntactical constructions with commas. If you missed a comma, the whole program would blow out. I mean, literally. So you're sitting there doing you got the drawings, and you're doing these takeoffs, and you're typing them in, and you're typing them in, comma, and it's very rigid, strict rules that are really obscure. And you make a mistake, and the whole thing blows up. And then you try to run it again, and the errors wouldn't always tell you like where exactly the error was. So you have to kind of look at the lines, and this is 11 o'clock at night, and you're exhausted, and you're trying to figure out where the problem is, and the project is due the next day. And then when you start it running, in the case of DO2, let's say it would take hours to run. So it was very user unfriendly. And so the big changes were to put user-friendly interfaces above or on top of these simulation engines. And that was kind of what I was trying to do with Comply 24 in the MS-DOS days, was kind of create a real simple interface that people could use. And actually people, the purists, the researchers in those days said, you can't, they sort of sniffed at it like, it's apples and oranges. You can't really make it simple. And I was saying, well, you can't make it simple if you're going to do a fancy analysis, but you can make it simple for people who want to do a simple analysis, which is what Title 24 generally is. So that was sort of a big leap for people, and we kind of convinced them that we had succeeded in that. In 98, we had a new round of standards. This is coming up to the present now. In the late 90s, big reductions in the amount of lighting energy that was allowed in the standards. Up until 98, they were still using the T12 bulbs as the basis for standards. That's only 6 years ago, which is pretty remarkable, even though the T8s have been around for, what, probably 15 years. But, so they've lowered the lighting allowances. There's also this tight duct technology. Has anybody heard about this stuff? A few people? Okay. Basically what happened in 98 is, let me take a step back. The Energy Commission in the 80s decided that the thing they ought to be doing is encouraging a performance verification of energy technology in buildings. So they created a whole shopping list of things, one of which is, it's called reduced duct leakage. This is basically a forced air with air conditioner system, if there's air conditioning, forced air system where the duct system, when it's installed, is pressure tested with nice fancy equipment, and that you can demonstrate and prove that the duct leakage is down to only 6% of the supply air fan or less. And if you can prove that, and then you have somebody who's not the installer come in after the fact who's certified and retest it to prove it was done correctly, you get this special credit. And that was started in 98. And there were some other things like that, similar kinds of things that required outside verification. No, not the building official. There's no way a building official is going to come in with a blower door and test. But this was kind of this idea that they wanted to get the industry to increase to raise the bar in terms of performance. And so they introduced all this stuff. The bad news was, because of the administrative and other costs, builders did not want to do this, so that nobody was using these credits in the early days, especially 98, 99 when the stuff was first introduced. I'm going to then talk, in a few minutes, talk about the current standards. What I'm going to do is take a moment here to say we've come a long way. So the standards basically work pretty well now, and they're actually enforced up and down the state differently, but there's a general acknowledgement building officials have to see the Title 24 forms, and they actually look at them a little bit. In some jurisdictions, they'll actually scrutinize them pretty carefully. So what happens is that homeowners, builders, architects, contractors, everybody realizes you have to do it right now, because the risk of getting caught, it's a high enough risk of getting caught that it isn't worth getting caught and having to discover you have to tear out $2,000 worth of stuff and change it. So that's really significant. I'll give you something I read once, that the British Air Force in World War II had to figure out how many airplanes they had to put in the air going in different directions for the Germans to give up on trying to essentially follow each one. So what they discovered is it was a ratio of 1 to 6. But what it meant is that if they could put up decoys, let's say 5 decoys, then the Germans would start realizing they have to start following, or up to 5, I think it was. They have to start following all of them to make sure that they weren't going to be bombed. This is a case where, if you can enforce the standards enough throughout the state, jurisdiction by jurisdiction, at that point you change behavior because people say it's not worth getting caught. There's an acceptance now. That's the other thing. Oh, in the early days, I'd have people builders coming into my office, screaming at me about energy codes. This is a waste of time, and this is ridiculous, and it's too costly, and we don't need this, and it's all bogus anyway. I mean, they were just, and I'd say, okay, but you have to do it. So you want us to do this? Or you want to go down the street and have someone else do it? They say, no, you can do it. They would just vent. They go crazy, some of them. I mean, not every day, but every once in a while we'd get this kind of real bad attitude. We don't get that anymore. We just don't anymore at all. I mean, people just accept, oh, you got to get a building permit, you got to go through this, and it's part of just getting a permit. So we've changed perceptions, we've changed behavior. The standards are really reducing energy costs. At the end of our presentation today, I'm going to show you some numbers of buildings that were built in the 50s or 60s, and comparing those buildings, how much the energy use has gone down, especially starting next year under the new code. So it's significant. The environmental impact, of course, has been reduced. And one thing I didn't mention here, although David Goldstein from NRDC mentions it often, is that I think California has, the lowest per capita energy use, one of the lowest or the lowest in the state. excuse me, in the country. That is, even though we have 35 million people, per capita, we are actually 50th or 49th in terms of, well, put it the other way, we're the lowest, or the second to lowest, of energy use per capita. And the energy code is not alone in that, but it's one of the major contributing factors to that piece of information. So I would say basically, to sum up the success story, I would say California has been very successful, and especially if you compare it to other states which are physically close to us in terms of climate. Washington, Oregon, Nevada, Arizona. If you look at the energy use in those states who border on California, and you look at the construction over the border, it's significantly different. Those buildings are using, I'm just guessing, 20, 25%, 30%, 50% more energy because they don't have building codes like California. So it's been really quite effective. Let's see. Yes. Yeah, it's a good question. I think the rough numbers, it's a chicken and egg question because market forces would have probably pushed the industry as it has in Oregon and Arizona and Nevada anyway. But if you ask the question, how much more per square foot do we spend in California than these bordering states who don't have as good as energy efficiency, I'd say you're talking about no more than $1 a square foot, and probably in many cases much less. That is strategic, well thought out spending on how to improve energy efficiency that maximizes the bang for the buck. Because the performance standards in Title 24, they push you to maximize your cost effectiveness of energy efficiency. So it's not a lot of money, and especially, I was having this conversation the other day, especially in relation to the cost of construction, which has skyrocketed, and the cost of real estate. So if you look at that now, I bet you the cost of energy conservation has gone down over time in relation to the cost, the value of the properties in which it occurs. I haven't seen that, but I'm sure of it. I've been at this a long time. So, let's see. I'm just going to skip ahead and okay. But I also want to mention, we're going to take a break in a couple of minutes. I want to mention a couple of things of those of you who haven't taken Chuck Clemens' course or may not. What's nice about the internet now and various kinds of technology is that all this stuff is at your fingertips now to download or look at, whereas in the old days you would spend months trying to order things and they would never come and everything was always out of date anyway. You have, the Energy Commission's website now, they have really good materials on obviously standards and related topics. There's a professional organization of building energy consultants which I helped found and of which I used to be chair several times, KBEC. And they have actually lots of information about training that's going on throughout the state, north and south. And there are certified programs which are available for both residential and commercial, non-residential occupancies under the standard. And so these are all available. And I guess what I wanted to say to finish up this segment was that it's hard to describe, as maybe Rocky alluded to, how much things have changed, and changed for the better, in terms of the integration of all these things. I guess the global science, the technology, the marketplace, the standards, the technology like the internet, all these things have created kind of a synergy in which we find ourselves. I'm still amazed at times when I really stop and think back. I'll sometimes go back and look at an old manual on the shelf, trying to throw things away, and should I keep this old thing? And then I start, daydreaming for 10 minutes or 5 minutes, thinking about, we were really in the dark ages then. It's like medicine today. If you know anything about medicine, how far it's come. And so I guess what I wanted to leave you with in the first segment was, we've come a long way. And also, probably, as Rocky points out, in the next 10 or 15 years, what we're doing now will look also somewhat amateurish and clunky. And hopefully some of you will be involved in those efforts. So I think this is actually, it's a good stopping point for a few minutes to take a break. And we're going to come back and we're going to talk about a little bit about the standards themselves and more about the current standards.
Okay, so quarter till, so 5:00, we'll kick it in again, 10 minutes from now.
Good. Okay. So what I always like to do in these sorts of talks is take a few minutes to just talk about what the standards do cover, in fact, because there's also a lot of misconceptions about that. And by inference, what they don't cover. Standards are kind of interesting things in the sense that you get somebody trying to get a building permit. And to get a building permit, you have the opportunity, which is true with all codes, building codes. You have this opportunity to scrutinize what's being built and look it over and approve or disapprove it. I'll digress for a moment in saying that, for example, codes do not go into effect. That is, the energy code does not, the state code doesn't take effect if someone's simply selling a building, selling a house, if a commercial building is being sold. Those are actually opportunities where a lot of us think there's a lot of potential energy savings. And in fact, the city of Berkeley, as an example, has a local ordinance, an energy ordinance, just within the city of Berkeley, where when any buildings are sold, the city intervenes and establishes that the building upon sale meets certain minimum mandatory requirements. So that's a kind of a local ordinance that's kind of unique. There might be some other places in the state that do that. But state energy codes are really around getting construction done, alterations, additions, and new construction. So that's the point at which we enter the process, or a lot of people like us enter the process, in terms of people having to get this analysis done. There are enlightened people in the world who wouldn't depend on Title 24 to do a good job and design a good building. But the reality is there's serious economic pressures on builders and homeowners and other people to put in the lowest cost everything to get a building built. So having standards is a form of regulation which makes eminent sense, despite the trends in the political world that go against regulation. This is where the tire meets the road. So just to give people a flavor of this, Chuck Clemens may have mentioned some of this in his class for some of you, but I want to go over because it's kind of important. It'll come back in a little later when I tie this together. Essentially, standards kick in when you have new conditioned space, at least for residential standards. So that space that's heated or cooled directly, or it's indirectly heated, which is to say it's probably insulated, enclosed space where the heated space opens onto it. There's some specific definitions in the code about it. There are some exceptions, historic buildings and temporary buildings. However, it's interesting that under mobile structures, the California Energy Commission is now moving to include relocatable classrooms as part of this. So the exceptions are becoming fewer and fewer, and that's the way the things have been going at the state level. Additions are essentially, this is definitional stuff, new floor areas and volumes, and legalizing old space. So what happens if somebody has a basement space that's typically unheated, and they want to condition it, they want to basically turn it into a family room, a game room, an office, home office, that counts as an addition under Title 24 because you're now creating new conditioned space. And what happens also in a lot of cases, just to give you a flavor of kind of the things that we experience in our daily life, is that a building official, if someone sells a house and the new owner or the seller says, this addition was put in 30 years ago, but it was never registered at the building department. And now the building official says, I have to show it meets Title 24 now, even though it was built in 1977. Well, it's a challenge. And so actually my informal advice to any of you is if you have a house or you have control over anyone or suggesting to anyone who's doing an illegal addition, don't do it. Legalize it, because the building officials are getting really tough, not just on energy code stuff, but everything. And they can really nail you. If you have done any kind of illegal construction and they discover it, it costs a fortune. It's a major deal. So Title 24 kind of plays into that a little bit. Now, alterations are by definition anything that's not an addition. And in the non-residential standards, you have, say, take this building as an example. I mean, it's a very unique building, but for this example, it's reasonable, which is to say you have the shell of the building, the external envelope of the building, and how it's insulated and so forth, including the skylights, the windows, and so forth. That's what's called the envelope. You have the lighting and the lighting controls, which is the lighting system, and then you have a mechanical system, some kind of mechanical heating. You do have mechanical heating, though, even though you don't have cooling, right? Radiant, okay, which is hardly ever used, probably, right? Right. Okay. So alterations in commercial buildings are kind of divided into these three disciplines. And in commercial buildings, you typically have architects involved with the envelope, obviously, electrical engineer with the lighting, and mechanical engineer for mechanical, at least in larger projects. So these things are kind of separate in larger construction, commercial, non-residential projects. And that's kind of the way that the standards are structured and the way they apply. Now, ever since the Warren-Alquist Act, going back to the 75 legislation, in that legislation, which I mentioned earlier, there's something called the Certificate of Compliance, which is a standardized form. This particular form in the residential code, is low-rise residential standards, is called CF1R. And basically gives you general information about the building and the energy measures that demonstrate that that building has met the code. And there's some addendums for special measures. And those sheets and those pages actually supposed to be on the drawings, on the architectural drawings, which are on record with the building official. So in theory, the idea was that you don't just meet the code, you have to permanently attach evidence of what measures show compliance as part of the permanent record of the drawings that go with that structure. In addition, the drawings also have to demonstrate, using a checkoff list, that you've met envelope, HVAC, mechanical, and lighting mandatory measures as well. So again, the basic concept hasn't changed in 25 years. It's the same idea. It's just been updated with each change in the codes. And that's what kind of has to be on the drawings. Now, what I wanted to do, to give you a better flavor for how the code really works in practice, I want to talk a little bit about what's called the performance approach. We talked about the prescriptive approach before. Prescriptive approach is you check off, you put into your building a whole list of insulation requirements and minimum glazing specifications and minimum mechanical efficiencies, and also maximum glass areas for houses, which are hard to meet sometimes. And if you meet all those requirements, you don't have to do any other calculations. Okay, what percentage of permit applicants use that methodology? In the residential standards, about 2%. In commercial construction, it's maybe 30, 40%, maybe less even. And there's a reason. The reason is, and this is also what makes California unique. It's called its performance standards. Most architects and homeowners and everybody who designs and wants to build things doesn't like to be restricted by the government dictating specifically each component of the building. And there are a lot of reasons for that. So what the performance standards were in the original Warren-Alquist Act is it said, here's the concept. If I take this building, if I take a design of this building, okay, I take the design of this building, and I put in the exterior walls just exactly the insulation required by the standard. Let's say R11 for commercial buildings in this climate zone, maybe R13. And if I put in the windows that just barely meet the U factor, heat loss, heat gain coefficients for the windows that are specified in the standard. In other words, if I just put in every single component exactly as the standard defines it, right? And then I simulate that, I do an 8,760-hour computer simulation of that building, where the computer simulation knows the weather temperature outside, it knows where the sun is, it knows the wind speed from weather data. It actually moves the sun across the sky, so it actually knows where the shades are and how much sun is getting in. It uses standard occupancy patterns of how often people are in the space and how many people are in there. It does all these things, and it comes up with an energy use in kBTU per square foot. Okay? That's what's called the energy budget. That means that my building, I can use less insulation or more insulation. I can change the glass area. I can change the efficiency of I can do anything I want within certain limits. And as long as I show my building uses the same or less energy than the building run with the energy measures, that means I pass. And it's really great. It's great because what it does is, in the real world, it says to builders and architects and everybody and clients, it says, how can you invest in conservation in this building in the most cost-effective way to reach a certain level of energy performance? Or to look at it another way, let's say you want to go for a PG&E incentive, which requires you exceed the code by, let's say, 15% or 20%. Or a LEED rating. People know about LEED. The Green Building Council has a special program. It lets you, again, make all these complicated trade-offs. And actually what it's doing is it's simulating the performance of that building in a much more real-world way than just filling out a checklist of what you have in the building. So it's actually giving you information. What it's doing is it's saying, gee, what if it's like a big chessboard, multi-dimensional chessboard. Well, what if I improve the performance of those windows over there? Just those windows. How much of a difference is it going to make over the whole year if I do that, or in my peak load? I can do that. In a few keystrokes in 3 seconds. Okay. Now let me see if I don't have this interior mass wall, but let's say I would like to pay to put this mass wall in, if it wasn't in my base case design. I can figure out how much this is going to cost, and I can figure out on the computer simulation how much it's going to save me. So you can start doing this incredible analysis of what if. Most of you sort of know about this, perhaps in some of your other classes. Well, the energy code itself has now taught the whole industry a whole methodology of analysis to evaluate buildings for real-world performance that sort of comes with the territory in terms of just showing compliance. In other words, you hire someone like us or like a couple of hundred other people like us in the state, or you do it yourself, but the bottom line is you learn a lot about energy performance in buildings because the simulations, although they're not perfect, are pretty close on average to the way the buildings are going to perform. And so you're learning about the interactive effects of all these design measures. Lighting, for example, lighting is a big ticket item, as most of you know in commercial buildings. You can reduce lighting 10%. It's going to outweigh almost all the other measures you look at. So it's an interactive tool. It's a self-tutorial interactive tool to learn about conservation. It's really spectacular. And that was actually what kind of got me interested in doing what I do, because I thought, if you can get a whole state of 35 million people involved directly or indirectly in this process, you're going to get better educated people are going to make better choices. And I think the standards have been doing that. So you have the so-called standard design and proposed design. The standard building is your building with the minimum measures, and the proposed building is your building as you actually design it with your actual windows, your actual lighting. And the performance method compares the two. And that's what passing or failing. It's real simple. It's not an A, B, C, or D. It's just pass, fail. And that's how the whole system works. So let me just stop for a second. If anybody has any questions or comments about this, this is kind of an important concept for what we're going to look at in a little while. So everyone sort of get the picture on that? Yeah, question?
How's the standard design specified? Is that strictly written out in the code? Or?
Well, actually, that's a very good question. The question is, how is the standard design translated into the computer software in a way that's clear? There's a whole manual called the Alternative Calculation Method, ACM manual. It's about that thick, 3 inches thick. It's the manual that the person writing the software uses to internalize within the software the correct rules that are defined in the standard. And as I said, I was involved in that contract with the Commission in 91, 92 when we did that for the non-residential buildings. So I'm pretty familiar with what's under the hood, but some of them are very obscure kind of rules. So it's a bit of a black box to people. But to get to the core of your question, in general, you open the standards to a few pages in the standard, and it tells you what the prescriptive requirements are, say for insulation. So in this climate zone, we're in climate zone, the state is divided up into 16 different microclimates. We're in what's called climate zone 2 up here. For commercial buildings, this is a commercial building. I'll look, and for wood stud, but these are concrete walls, or there's some wood stud in there?
These are actually SIPs.
Okay, but they're wood panels. Well, they're wood, right. But this would count as a wood stud. Okay, this building would be compared to a standard wood stud construction in which the walls had, say, probably R13 insulation. So the software would use the R13 value in the walls when it simulated this building to set the standard design, see? And it tells you what the windows have to be. But then this building would perform way better, 75, 80% better than Title 24 at least, because it's got all this fancy, wonderful stuff in it that performs much better. So so you're doing a really rigorous, scientifically accurate side-by-side comparison of the, apples-to-apples comparison of the same building. And let me just say again, that was the big breakthrough in the code. And no other state quite does it this way, or even ASHRAE 90.1 doesn't do it this way. That's the national code. We really have used a scientifically rigorous method. How the political process allowed people to end up with a really legitimate method, I'll never know. It's really sort of amazing. Because usually politics distorts everything. But this is a case where we proved that we could get this to work, and it made sense. And it sends, I guess here's my bottom line about this, and then I'll sort of move on. It sends the most truthful message you can to building designers about the impact of their design decisions as part of meeting the code. And to me, whether it's, some of you have read Lester Brown's work, Plan B, and Lester Brown's saying on the larger global scale, the global economy has to send the truthful message about the ecological impacts of economic products and services and decisions to have a sustainable global ecosystem. If you don't honestly take into account the embedded value of forests and all those things, and you'll never have an economy that works. Well, in the sort of smaller version with building energy conservation, you have to send everybody, the simulation sends the accurate message to the architect. You do this, this is going to happen. You do that, that's going to happen. And that's kind of built into the process, and that's the beauty of it. That was kind of the vision a lot of us, about 10 or 20 of us about 20 years ago, were kind of all trying to work on, because we thought there's something in here, because it's not just a paper chase. There's a reality underneath it that really has value, and so that's kind of what's kept us going. All right, let me move on. So here's an interesting question. If everything is interactive, and especially if you're in a kind of an interesting microclimate that's kind of mild, what is an equal better architectural specification? Let's just say I simulate this building performance with a certain kind of glass, right? Is a better shading performance glass better or equal? Or is something that lets in more sun in the winter that heats the building better? You see where I'm going with this? Because you figure some insulation is good, more insulation is better. That's usually true, but that's not always true. And the reason it's not always true is because if you have mild climates, which we do in California, sometimes it's better if there's less insulation because heat will actually escape at a time of the day where you can use that to pre-cool the building for the next day. And so there's some sort of tricky issues in here, although common sense usually holds. But there's some interesting sort of technical questions. How much of a difference in the outcome do certain measures make? For example, if a builder is supposed to put a certain glass type and he doesn't do it, does the building still pass? And who's going to go back and check it? We do this sometimes. A building official catches somebody and says, they put in all standard. They didn't put in low E windows. What do we do? I said, well, let's just rerun it with the lousy windows and see if it still passes. I mean, we actually reanalyze it. But there's sort of these kind of questions. And then what's the compliance margin? And this has to do also with special programs, incentive programs. The beauty of the performance approach is if you just pass Title 24 and you keep going and do better and better, these incentive programs give value for 10% better, 20% better. PG&E is giving really huge incentives for buildings that exceed Title 24 by 30%. So this building would be a slam dunk in anyone's book. But there are all these other related questions. Okay, so let's move up to the present now. What are the standards now? Well, what happened is recent history back in September of 2000, there was emergency legislation under the former governor, Gray Davis, from the San Diego and other power crises to suddenly say to the Energy Commission, we've got an energy crisis. We want you to now use this crisis as an impetus to kind of cut peak loads even more. So the goal specifically in the last round of changes, which was developed in 2000-2001, was to cut peak electric load for obvious reasons. The Commission approved this in 2001 very fast, took effect in June 2001. And these codes that are called the AB 970s, that was the Assembly Bill 970. That's why it's called AB 970. That will be in effect until next year, till October 1st. So we have about 4 years here in this current set of codes. these codes now made this reduced duct leakage, tight ducts thing that I explained before. It makes it as the standard measure in new houses, in all new houses, in all 16 climate zones. So if you don't want to build a house with these tight ducts, you can do it, but then you have to trade off and put something better into the house because you're not doing this thing that's now a, quote, standard requirement and the prescriptive requirement. So all new forced air systems, you know, are involved in this. And there's this thing called a HERS rate, or a home energy rating system. This is a generic term. When these tight ducts are put into a house, this person comes in, they're certified, they have to retest the duct system. And there are other measures too we'll talk about in a few minutes besides tight duct. The low E, low solar windows are now essentially standard in all the cooling climates. So this is considered a cooling climate, climate zone 2. Actually, in 2001, they moved Sonoma State University, they moved the weather here from a moderate climate, they're now calling it a severe climate. So what they did is they said there's enough cooling in this climate that we ought to put in much more efficient windows, much more efficient air conditioners, and so forth. So where the other climate zones say maybe they were 15% tougher in the change in the standards, climate here it's 25%. There's a big jump of 25% more energy efficiency in one code cycle in Sonoma, in Santa Rosa, in Marin County, and Sonoma, you know, up and down the coast here, as soon as you get away from the water. Thermal expansion valves. This is kind of an interesting, I mean, building conservation is often a collection of a lot of little things. Here's a little popular mechanics gimmick. It turns out that air conditioners, which have coolant, Freon, change their efficiency dramatically based on the pressure of the, based on the temperature, outside temperature, because the pressure of the Freon in the coils is a function of outside temperature. Well, it turns out somebody figured out if you could control with a valve the movement of the Freon in and out of the coil, just by having a little valve, a $50 valve, you could improve air conditioning performance 9%. And 9% is actually nothing to sneeze at. That's pretty good for just a little $50 part. So this is now in the standard as a requirement. Radiant barriers, this is if you have a roof, which is, let's say, a big plywood, roof, and you have an aluminized reflective surface, which is really a low emittance surface, it helps keep the heat of the roof out of the attic in the summer, and it helps keep the heat in the house in the winter, and that's 25 cents per square foot roughly additional cost. So these pretty modest, costs for some of these things. High performance windows, those are low E windows. In non-residential changes, so that was residential. Back here, that was houses. Here, in commercial buildings, this is a big ticket thing. For some reason, the commercial standards had foot dragged on forcing high performance windows for many years. In 2001, the commission came down with a vengeance and really radically changed the whole idea of what kind of windows you put in commercial buildings in California. Low E coatings, incredibly high performance windows. Low power densities for lighting. And now, we don't have any offices in this building, do we? But offices are assumed to have a certain percentage of watts of lights from task lights, from plug-in lights, which we didn't before. There's some other things that happened about duct insulation and duct sealing credits for packaged rooftop units and some other little things. But anyway, the non-residential standards really got squeezed. And again, if you look at most of these things, these are things that are going to do what? Reduce air conditioning loads. That's the big thing that they're looking at. The big power crisis in 2000, 2001 put the fear of God into everybody in terms of peak power. So we're trying to do everything we can to reduce peak electricity use. Okay, so let's stop there. Any questions about current standards? We're just floating around here. Comments, questions? Okay. Yeah.
I don't know if this doesn't fit in to what you're talking about now.
It's okay.
But I wondered if it's possible to put in as part of the standard, the increased solar savings fraction to to basically effectively require people to use some either thermal, solar, or photovoltaic in new construction? That was the first question. And the second question is, we're taught in this program that basically it's possible to make buildings energy net zero energy, and that's really where we want to go as far as global warming and all that. And do you see this standards type approach moving towards that, to where buildings are going to eventually be required to be zero energy?
Yeah, I think I'll take the questions. I'll repeat briefly for the record. The two questions are about solar thermal and some solar photovoltaics, relevancy and usefulness, and what I think about that. And the second question is whether going to zero energy use buildings is practical and really desirable and so forth. Let me start with the solar question. I think solar thermal and solar PVs are different things entirely. Because actually one is a demand side issue to some extent. And solar thermal, although it's producing hot water, it's really integrated with sort of the demand side in terms of basically adjusting what's necessary after using solar. The problem with solar thermal collectors is that there's nothing really wrong with them. They're still a really good idea. But by the time you get a collector on a roof, let's say, as an example, there's issues about long-term viability, maintenance, repairs, and if there were a solar collector system that was as common as a standard auto or a standard widget that everybody had, so there was a big thriving business on maintaining and repairing the same kind of unit, the cost would go down. The problem is that there isn't such a thing at the current time. Also, natural gas, even though it's not exactly cheap now entirely, it's still cheap enough that warming water with a high-efficiency water heater system is pretty inexpensive compared to the first cost. So you have the first cost issues, which are deterrent. And also, there just simply aren't the tax credits available from the state or the feds that there used to be. So I would say the payback, if you have a house which has natural gas on site, the payback is still maybe 15 to 18 years, or something like that. Now, if you live in a house, I'm going to, in front of God and everybody, say that I live in a house that's an all-electric house. That's because my whole subdivision was built in the 70s it's right next to the Hayward Fault, and they were concerned about natural gas. So in our subdivision, actually, the payback is probably 6 or 7 years. It's probably viable. And I'm the president of my homeowners association. I'm trying to work to put that in. That's thermal, though. Now, on photovoltaics, I heard Severin Bornstein on Forum this morning. He's the energy guru at UC Berkeley and is on the news and talk shows every week. And he was asked this morning about alternative energy power generation, wind versus PV. And the way he framed it is the way I understand it as well, and he's the expert, which is that wind power is, large-scale wind power generation is very cost-effective now and competes really well with the most cost-effective high-efficiency natural gas plants. But solar photovoltaics is still expensive, and so the return on investment, it's still a long payback. It's a really interesting technology. They're still working on it. If anyone wants to do it, I applaud them. It's a good thing to do for the environment, but it just doesn't have the economic payback of other things. So I hesitate. If I'm advising clients, I basically say, if you've invested your money in the house and all these other really cost-effective ways to lower your energy use in your house generally, then I'd say if you still want to do solar photovoltaics, great, let's go for it. But I think that money was better spent on some other technologies first, almost universally, with very rare exceptions, right?
Yes.
Okay. You agree? Yes. All right. Well, that's good. We don't have to agree, but that's good. On your larger question about zero energy use, I think that it's always been the holy grail, and I think in demonstration projects like this building and certain homes that the utility companies have sponsored, I think it's great to demonstrate that these things are possible. But it's the same issue. It's a cost-effectiveness issue. How far do you go towards energy efficiency before every $1,000 more you spend will reduce a smaller and smaller return on investment? And it turns out that you can be titled. Let me give you an example. Well, maybe I'll address that in here. But let me just say, in general, it's not cost effective to go all the way, but it's becoming increasingly cost effective to go further and further. As technology improves, as these things become more and more common, it will become more common generally. So that's sort of the answer. It's an incremental process. And in 15 years, I might give you a different answer, or 10 years, than I do today. But today, it's still not worth going all the way, but it's definitely worth learning about how to do it, because it gives you insights into this equation of what's cost effective. Now, that was a good question. There was another question or comment? Did someone need to ask? Or? Okay. Well, this next view graph addresses this issue quite nicely, so thanks for that question. What this was kind of a little study I did 2 years ago before I came up here at that time, looking at a 50s house in Rohnert Park and assuming that the building was built to what was considered market standards in those days. In those days, this is 50 years ago, no wall or floor insulation, R11 in the attic, single, clear, maybe wood, maybe metal frame windows, water heaters which were not especially efficient, relatively inefficient furnaces, inefficient air conditioners, and no duct insulation. That was actually how things were built. If some of you may actually be renting in an apartment or a house, which there's still a lot of infrastructure left. 78 was the year the codes took effect, and the code said, okay, you have to put at least R11 in the walls, R19 in the attic. It improved the efficiency of some of the mechanical equipment and some duct insulation. And that was considered a really radical thing. That was, shaking the cage of a lot of builders in those days. In 1999, using the 98 standards, the same house would have R13 walls, R19 in the floor, R30 attic insulation, dual wood frame windows or vinyl, high efficiency mechanical equipment across the board, and higher duct insulation. So this is kind of giving you a sense of what was happening. And today, it's basically the same as 98, except you have tight ducts. We just talked about that. A little higher efficiency water heaters. And I put Marvin Lowy, you have better windows today, typically, on average, than you did 3 or 4 years ago. The code is pushing it. The code's driving it now. And next year, you're going to have an even more efficient house, because I said, remember, the code's squeezing things down with much more wall insulation required, much more, and there's something else I'll mention too, but that's in a high efficiency air conditioner. The federal appliance standards are going to change in 2006. It's going to increase efficiency of water heaters and air conditioners. Okay, so what are the results on this? Well, I did a little simulation using the standard software that we use for compliance, and these are standard assumptions. And the 50s house was using 225. It's 1,000 BTU per square foot, and that's source energy, by the way. And then in 78, that was reduced probably in half. The first energy codes reduced that in half. And you can see all the way down, and by next year, 2005, that will be almost 80%, approximately 80% reduction in energy use from the house built 50 years ago. So that gets to your question, how far do you go? Well, in 50 years, really only 25 years since we started forcing people. So in 25 years, from what was going on before, we've gone an enormous distance. Yeah, continuing question.
So the next question to me after this is, well, there's still a lot of 1950s and older houses out there, and what do you do about those?
Right.
This is great for new construction.
Right. That's the $64 question. The question was, so what do you do with all this existing construction? Because unless someone does an addition or alteration or a gut rehab of the house, the local building department's not going to get in there and scrutinize it and make them meet a new standard. And that's a question the Energy Commission is studying. The Commission is studying, for example, I would say when a house sells, okay, follow this, when a house changes hands, it's reasonable to assume that attics, which are easily accessible, should be insulated to R30, right? It's $1 a square foot. So a 2,000 square foot rancher. So when someone sells it for now, what are houses selling for here? $400,000, $500,000, $400,000. Okay, so they can spend. Someone, either the buyer or the seller, can figure out. And my view would be give them 18 months from close of escrow. So if it doesn't happen at sale, they have to. But in any case, forget the rules. Spending $1,000 or $2,000 to insulate the attic is an enormously cost-effective move and makes perfect sense for public policy. Yeah?
I just would suggest that people get involved politically with their planning departments and city councils and require that any new development provide for mitigation for the increase in power and energy consumption within the community by doing programs to weatherize existing homes, install fire efficient furnaces, water heaters, windows, and you put the onus of that on the developer, saying, hey, yeah, you want to build in here, you have to take care of this because we're concerned about blah, blah, blah.
Right. The comment is generally, people should get involved in local politics because you can have local ordinances which exceed Title 24. Title 24 is a statewide minimum, but there are local ordinances which by the way, the Energy Commission has to approve them because they want to make sure that the ordinances, in fact, exceeds the state code. That's important to them. They don't want any weakening of the code. But that's a good point. So here you have an enormous reduction in energy use in 50 years, and I said really in 25 years since the code took effect, really. So that's sort of an example. Now, what's going to happen in October is next October. This is 2005. Here's the big thing. This is, if you've fallen asleep, wake yourself up now because this is actually a key concept. The big change that's occurring is the first change since 1975 in assigning a valuation of electricity in relation to natural gas. So let me explain. The 1975 Warren-Alquist Act said the source energy multiplier of electricity is 3. That means for every 3 BTUs that a power plant in, Folsom generates to create electricity, 2 of those 3 BTUs gets lost on the way to this building here in Rohnert Park. So there's only a 33% source energy efficiency of electricity because between combustion of oil or gas or something to make the electricity and the transmission line losses, you're losing 2/3 of it before it even gets to the building. So the environmental impact is not good. So there's been a 3-to-1 multiplier. So that's why electricity is hard to show that it passes the current code. But here's the thing. What happened in the recent energy crisis with power, peak power failures is that the Commission said we want to actually lessen the penalty of electricity if it's in the middle of the night, if it's off-peak, and we want to increase the penalty to more than 3 if it's August and 4 o'clock. So we want buildings that are designed such that the simulation of how they meet the energy code, it's called time-dependent valuation, TDV, that's the acronym. And it's using an old established concept that the utilities have used for years for commercial clients called time of use rates. The utilities charge large clients much more per kWh for peak electricity use than off-peak. Well, it's essentially embedding that idea into the actual simulations that the energy software is going to use to show compliance. So what is that going to do? And how is that going to change the credits and penalties of heating versus cooling in the codes? Anyone wants to venture a guess? Yeah. Right. Correct. Air conditioning will be hit harder, and heating will be essentially a little bit more forgiving. There'll be a little bit more forgiveness and flexibility about heating because peak power demand becomes much more of a driving force in what's appropriate and what's the defined standard or norm. So that's going to be a big change, and it's going to be changed for both residential and commercial buildings, all buildings. And it's going to shake up the building industry in terms of what we do because they're going to be shocked, especially in climate zones like this where you have a moderate amount of cooling, not always, but you have, 25-30% of houses have cooling, something like that. But in places like Sacramento, Palm Desert, they're going to go nuts. So it's going to be a really big change in the code. And it's going to, it's only going to affect change over, it's going to take 15 or 20 years before all this new construction under the new code really, establishes a large proportion of the buildings in the state. But over 15 or 20 or 25 years, this is going to have a big impact. The other thing is that there are new federal appliance standards which are taking effect in 2006. The Bush administration sued to try to have them overturned or delayed unsuccessfully, and Natural Resources Defense Council looks like they're winning their suit or they've won. And so it means that air conditioners, which are now minimally a 10 SEER rating, and you can buy 12 SEER pretty easily now, 13 will become the norm. So it's actually going to be a standard which is actually slightly above even the slightly better efficiency ones that are sold commonly now. So that's going to raise the bar, and water heaters as well. Oh, this is a big one. Lighting power densities are going to be reduced, but also they're going to be, for the first time, standards for outdoor lighting in parking lots, parking structures, signage. I mean, maximum amounts of watts you can use outside of buildings that are not designated security areas and theater. You know, there are certain exceptions for certain things, but this is going to completely change the way that landscape architects and other people design out. Because right now, under the current codes, outdoor lighting is exempt. And even lighting in enclosed spaces, which are not heated spaces. Like if you have a warehouse, which is not being heated, the lighting in that space is exempt from the code. But under the new standards, any enclosed space and outdoor lighting will all be considered fair game. So they're squeezing every, their tentacles are trying to reach into every thing that they can, which is good because, why not? It's possible to regulate at permit. Relocatable public school buildings. Let me tell you a quick story. I've got a few more minutes left. Here's an interesting story. In 25 years, this is the state has what's called the Division of the State Architect. The state directly oversees the construction of public school buildings, K through 12, okay? So the state is the one responsible for energy efficiency in schools. They've never enforced the energy code in 25 years, except they started last year. Why? Because the state legislation approved energy efficiency grants to schools that exceed Title 24 by a certain percentage. So people like us said, yeah, they're giving away several dollars a square foot, which is, it's a lot of money. Say a 50,000 square foot elementary school might get a $125,000, $150,000 grant, energy grant for energy efficiency. I mean, the division of the state. What it is the state gives away construction bond money, right? And so construction bond money has a rider attached. Essentially, it's an add-on to the normal construction bond. You have to meet the Office of Public School Construction guidelines to get the regular school construction grant that the state has been offering for 100 years. But there's an extra. It's called Prop 47. It passed in 2002. You get a Prop 47 energy allowance grant, and you get a lot more money, and not just for new construction, but for modernizations. My daughter, who's 8.5, goes to a public school in El Cerrito, Bay Area, and the school district, West Contra Costa, which is otherwise broke, but basically is rebuilding its 51 schools. And we demonstrated on her school. I volunteered, through PG&E, I worked out showing the school district that for her elementary school, they could get a $50,000 grant for paying me basically $5,000 over a whole long period to do all this analysis and reporting. And so they paid me $5,000 and they got $50,000, from the state. And as soon as I did one, they go, hey, this is great. And they signed me up for a whole contract. So now I'm their energy coordinator because I showed them that they're making money on energy efficiency. And public schools are suddenly, because they're going to give money to exceed the code, they said, well, we better start checking ordinary schools to see that they meet the code. So now suddenly they set up a whole energy division in the DSA to start plan checking schools. So it took 25 years, but now they're actually doing it. It's really remarkable. So this is where, also, didn't talk about carrot versus stick. This is where the energy code is the stick, and then there are all these carrots. And the carrot of PG&E programs, of Prop 47 funding, of LEED, of CHIPS. There are all these special programs. And in this case, the carrot got the state to enforce the stick. So this is kind of an odd, it's a kind of a backward situation, but it worked. And it's really great. And this will continue, I found out, indefinitely into the future. They've deemed it a success, and they're going to keep going indefinitely. So this is a whole new market opportunity for our firm. So we're, yeah.
Well, water heaters, aren't the on-demand ones significantly more, aren't they don't they use significantly less power?
Yeah, I mean, the question is essentially instantaneous water heaters. But there are two kinds. There are electric resistance and there are natural gas. Now, even the electric resistance ones use less energy than the tank, 50-gallon storage tank electric resistance, obviously. But the highest efficiency are the instantaneous gas, the Aquastars and the Takagis, and And they're not cheap, but they pay for themselves in about 3 or 4 years because there's no tank loss. So, yeah.
So why don't they just do the standard that they all have to be on demand starting in 2006?
Yeah, the question is, why don't they put it in the standard? Because what they put in the standard is, unfortunately, still fairly political. If someone can demonstrate that these water heaters are cost-effective, then in theory they can put them in the standard as the baseline. But there are a lot of reasons why they hold back on putting everything into the, every cost-effective thing into the standard, because there's some politics about enforcing a very high level of efficiency beyond what the market is used to. So that each code cycle they keep making it harder and harder, but they don't load it up. Maybe in 2008 they'll consider it. In fact, I'm going to a workshop in 2 weeks at PG&E, and I'm supposed to write up ideas for improvements, and I'll throw it into the hopper for you. So we'll see what happens. Yeah.
I've heard that these standards committees, or the committee that creates the standards, is typically loaded with like industry representatives, and that they pretty much direct what's going to get in and what is out. Is that your?
Yeah. The question is, does the industry have undue influence over what gets into the standards? I would say the answer is yes and no. There's definitely significant industry representation and influence, which shapes a lot of decision making, some of which is actually very good, very reasonable, and some of which is dubious. So it sort of depends on the specific technology and the policy issue. So it's kind of a mixed bag. So it's yes and no, I'd say. Let's see, a couple more minutes. Let me wrap up here. So my final thoughts are that we all individually make a difference in different ways. Some people may be involved in or be maybe exposed to research and so forth that's going on. Policies, so this discussion we were having about what local jurisdictions can do, it isn't all about technology. Technology is there, and it's on its own track, continually creating new possibilities for energy conservation. But the policies and the programs are really important too, because despite what free market ideologues say, technology just doesn't magically get into buildings on its own. You need regulation, you need policies, you need programs to really facilitate and encourage energy efficiency from ending up in buildings and people using it. But lastly, individuals make big differences when it comes to voting for candidates. And who gets into office, of course, does make a big difference at every level, national, state, and local. So apathy is not a good energy efficiency strategy. I think being a participant is better. And with your wallet, because whether you're a renter or you're a homeowner, you probably own a car, so there's an opportunity there. There are all these different opportunities, and if you're an Amory Lovins believer, which I still am. How many people know who Amory Lovins is? Okay, good. So Amory's point is that, common sense energy efficiency is cost effective. And that's what he spent his last 25, 30 years trying to show, and I basically agree with it. So using your wallet wisely is probably a good energy efficiency strategy. Just a couple of final notes. Looking beyond the current and future standards, I talked about the City of Berkeley's ordinance already. Some of you who are activists might be interested in that. I can give you more. You can actually, the City of Berkeley has a website. It's the RECO standards, RECO, Residential Energy Conservation Ordinance. You can look it up on their website. And Marin County now, this is something interesting. About 2 years ago, the planning director of the county of Marin came to me and said, would you like to write a new energy ordinance for us? I said, sure. What is it going to be? And he said, well, the Board of Supervisors had approved a vote which said that they wanted new homes in Marin County, not in the city, not in the local, but the outlying, the unincorporated areas of Marin, that are larger than 3,500 square feet. They wanted those homes to use no more energy than a 3,500 square foot house. In other words, a 7,000 square foot brand new house would only use the same energy as the same house built to 3,500 square feet. It was an interesting intellectual problem, and I think we solved it really well. And it took effect a year ago, and it's been working out really well, apparently. First of all, what they wanted to do was actually control the size of new homes. And they felt if they squeezed people on the energy issue, people would say, well, let's just make the house a little smaller because it's going to be too hard to meet this requirement. And I had to go through the whole process with the Energy Commission, demonstrating that it was cost effective and so forth. And apparently it's working fine. They have, I mean, I called them a month or two ago. I said, well, is anybody suing you yet, or is anybody complaining? And they said, no. Of course, it's Marin County, but still. And by the way, this actually we figured out a way to give credit for solar photovoltaics. In other words, you had to meet Title 24 without the PVs, right? But to meet the county ordinance, if you want to use PVs, we figured out a methodology to give appropriate annualized credit for photovoltaics on the roof. And that's the first time any energy code has done that, at least that we know in the country. So it was kind of interesting. And finally, I'll end the talk where I started, which was, the realities keep shifting. I mean, the basic core phenomena continues unabated, unfortunately, in some detrimental ways, like Mideast oil and Mideast politics, global warming, and discouraging political events and policies. On the other hand, the positive side is that crisis and opportunity are the same character in Chinese, and I still keep hoping that with every crisis there is opportunity. And in fact, the past 25 years has shown with each crisis there has been great opportunity, which a lot of us have taken advantage of, to make the standards and make building conservation and all kinds of conservation much more viable. So I'd say that don't lose hope and don't lose heart, and keep working, and we'll get there someday. Thanks very much. You want it? Okay.